Welcome back. I'm Muggsy, and today I'm going to explain mole ratios. Before you learn about mole ratios, you should know how to represent a chemical reaction with a chemical equation, and you should also be able to balance that equation. After we learn about mole ratios today, you'll be able to actually dig into stoichiometry, which is the real core of chemistry. And once you know stoichiometry, you can pretty much do anything in chemistry. So let's jump right in. What if we had some hydrogen gas and we reacted it with some oxygen gas, O2, and they created steam, H2O. Hopefully you've noticed there's a problem with my chemical equation that I just wrote down. And that is, we have two hydrogens in the reactants, we have two hydrogen atoms in the products, we have two oxygen atoms in the reactants, we have one oxygen atom in the product. This is an unbalanced equation. So let's just balance it really fast. If we put a 2 in front of this H2O, we now have two oxygens, so our oxygens are balanced, but we have 4 hydrogens in the products. So in order to get 4 hydrogens in the reactants, we just put a little 2 in front of this H2 here. Okay. So, if I wanted to make a specific amount of water, I could think of this as if I had two H2 molecules, tiny little molecules, and I combined it with one O2 molecule, I could make 2 water molecules. That's great, that's all well and good for conceptualizing what's going on, but it's pretty much impossible to do that. These molecules are unimaginably small. And so there's no one on Earth who's actually done this reaction of taking 2 H2s and 1 O2 and sticking them together to make 2 H2Os. In reality, we need a large amount of H2s and O2s, but we want to keep these kind of ratios the same. So instead of making 2 H2 molecules, we could take 2 moles of H2 and react it with 1 mole of O2, because there's no number here, so it's 1. And that would make 2 moles of H2O. Because in order to get these numbers, I'm just looking at the coefficients in front, right? And now I actually have some reasonable numbers, because 2 moles of hydrogen gas is a little bit more than 2 grams. 1 mole of oxygen gas is something like 32 grams. 2 moles of water would be like 36 grams. So these are actual quantities that we can work with. So the mole is this massive number, 6.022 times 10 to the 23rd, Avogadro's number of atoms. And the whole point of the mole is to be a really big quantity, bigger than a pair or a dozen or a century. This massive quantity, so we can have relationships between atoms, and we can actually work with manageable quantities in the lab, grams or milligrams or kilograms, instead of this incredibly small number, you know, way smaller than femto, pico, nano, all that stuff. Incredibly small amount of mass. Okay, so the mole ratio is just the relationship between our different reactants and products. So if we were to ask for the mole ratio between H2 and O2, we would say that ratio is 2 to 1. If we wanted to do it in reverse, I guess I should draw an arrow there. If we wanted to do it in reverse, then that would be 1 to 2. The important thing here to consider is, what if we had a relationship between H2 and H2O? What's the mole ratio there? You might say 2 to 2, but those of you who are math literate would probably have hit on something important, and that is ratios should always be simplified. So instead of 2 to 2, we can divide both those numbers by 2 and call this ratio 1 to 1. If we started with 1 mole of H2, we'll end up with 1 mole of H2O. Okay, let's do another equation. We'll go over the mole ratios, and then we'll start actually using these mole ratios to predict how many moles of a product will be produced for a certain number of moles of reactants. Here we have the combustion of ethane here, the fuel source, which is burned in the presence of oxygen to produce carbon dioxide and steam. Ethane, you might also call it dicarbon hexahydride, but if you know about organic chemistry, we call it ethane. Okay, hopefully by now you've keyed into the problem with this chemical equation up here, and that is, again, it's unbalanced. So let's just balance it really quick. We've got 2 carbons here in the reactants. Let's put 2 in the products. We've got 6 carbons here in the products, reactants. Let's put 6 in the products. Now let's check our oxygens. We have 2 times 2, which is 4, and we have 3 times 1, which is 7. Now that's going to be a problem, because if we have 7 oxygens here in our products, how many groups of O2 will give us 7? Well, 7's not divisible by 2, right? It would take 3.5 O2s to give us those 7 oxygens, and you can't have a fraction of a molecule. So whenever that happens, kind of find your biggest thing and just add more of it. So we've got this ethane here. We've got 1 of them. Let's just make 2 of them now, and we'll update everything else. So 2 times 2 is 4 carbons. Let's make this a 4. And that gives us 2 times 6 is 12 hydrogens. So in order to get 12 here, we're going to need a 6 here. 6 times 2 is 12. Now let's count up our oxygens. 4 times 2 is 8. 6 times 1 is 6. 8 plus 6 is 14. 14 is divisible by 2. How many groups of 2 give us 14? 7. And now we have a balanced combustion equation for this reaction. Okay. So let's look at our mole ratios. For every, let's look at the mole ratio of our ethane to oxygen. So for every 2 ethanes, how many oxygens do we need to burn with it? We need 7. Let's look at the mole ratio of ethane to carbon dioxide. For every 2 ethanes, there's 4 CO2s. But that to me looks like something that can be simplified. We would call that 1 to 2, because both of those are divisible by 2. And same thing with our ratio of ethane to water. We've got 2 to 6. 2 to 6 simplifies to 1 to 3. Now remember, a ratio is directional. The first number in the ratio tells you the first thing that you're talking about. So if we were to do all of these backwards, like water to ethane, for example, we basically just flip the numbers. That becomes 3 to 1. CO2 to ethane would be 2 to 1, and O2 to ethane would be 7 to 2. Now, why didn't we simplify this one like we did the other ones? Well, because 7 and 2 aren't divisible by a common factor. Okay. So hopefully mole ratios is pretty simple. It's just like doing any other ratio in math class. What's going to be a little bit different now is we should be able to use this information to actually answer some math problems about stoichiometry, essentially, about how many of these different reactants and products we're going to need and how many are going to be produced and all that kind of stuff. So for instance, what if I had 10 moles of ethane and I burned it, the reaction happened, how much steam is going to be produced? How much water? Well, in order to get this problem, all we need to do is figure out the mole ratio between our ethane and our water, and we can see that's 2 to 6, which simplifies to 3 to 1. And then it just becomes a conversion problem. So I would write it out this way. If I had 10 moles of ethane, C2H6. I want to get rid of moles of ethane. I want to figure out my moles of water or steam. What I put in this conversion factor is the mole ratio. We know for every 2 moles of ethane, there's 6 moles of water, or for every 1 mole of ethane, there's 3 moles of water. We're using the mole ratio in our conversion factor. And now it becomes a really easy math problem. 10 times 3 is 30. 30 divided by 1 is still 30. Moles of ethane cancels with moles of ethane because it's on top and bottom, leaving moles of water. So now we can actually quantify some things in our chemical reactions. If I started with 10 moles of ethane, I could tell you that I'm going to produce 30 moles of water. And it's 3 times more because of the ratio to these things in the chemical equation. We're going to produce 3 times more water than we are ethane because the ratio is 3 to 1. Let's do another example real quick. Let's use that same number, 10 moles, why not? If I have 10 moles of ethane, how many moles of oxygen am I going to need to fully burn with those 10 moles of ethane? So now we're kind of looking just at the reactants. If I have 10 moles of this, how many moles of this am I going to need to do a complete reaction? So again, we basically just use our mole ratio, and our ratio of ethane to oxygen is 2 to 7. It can't be simplified because 2 and 7 aren't divisible by a common factor. So we take our 10 moles of C2H6, we draw a blank conversion factor. We're going to put our mole ratio in here, but before you put the numbers in, I always recommend with my conversion factors, just put the units in first. So moles of C2H6. And it's important to write what it is we're talking about, because if not, I would just have moles on top and moles on bottom, and that wouldn't be very useful. But if I put moles of C2H6 on bottom and what I'm trying to get, moles of O2 on top, now all of a sudden this conversion factor makes sense. And now I just need to look it up and see that for every 2 moles of ethane, I require 7 moles of O2. And now it just becomes a simple math problem. 10 times 7 is 70. 70 divided by 2 is 35. Moles of ethane cancels with moles of ethane and leaves moles of O2. Okay, we'll look at one more example, and then I think you'll pretty much have this concept pretty well in hand. Here we have the single displacement of magnesium bromide by sodium metal. Basically, if you have a solution of magnesium bromide, you put in some solid sodium metal, that sodium's going to go in, kick out the magnesium, and you're going to be left with sodium bromide and free solid magnesium. You'll learn about these different reaction types later. The important thing here is, hopefully by now you've noticed, it's unbalanced. So let's balance this sucker. We've got 2 bromines here in the reactants. Let's put 2 bromines in the products. Now we also have 2 sodiums in the products, so let's put 2 sodiums in the reactants, and we're balanced. This was an easy one. Okay, so let's do a real quick problem. If, for example, I had, let's say, 17.5 moles of pure sodium metal, how much sodium bromide am I going to make? How many moles, I guess I should say. Well, if you're smart, you've probably picked up already that the answer is exactly the same, 17.5 moles. Because we're looking at the relationship between sodium and sodium bromide, and we see that ratio is 2 to 2, which simplifies to 1 to 1, which means however many we have here, we're going to have that exact same amount here. So if we used 17.5 moles of sodium metal in this reaction, we're going to produce 17.5 moles of sodium bromide. That was a pretty simple one. Let's look at like a slightly more complicated problem with this same reaction. And let's say that this reaction produced, let's say 50, why not, moles of magnesium. We want to know how many moles of sodium were required to do that. So if I want to run this reaction and get 50 moles of pure magnesium metal out, how many moles of sodium metal do I need to put in? Now, in this case, we're going backwards from the reactants, but we still set up our problem exactly the same way we did earlier. So start with what you have, and that's 50 moles of magnesium. Multiply that by a conversion factor. Put what you want to get rid of on bottom, and that's moles of magnesium. Put what we're trying to get on top, and that's moles of sodium. And now we just put the relationship between these two things that makes sense. I'm feeling a little dizzy. I might make a mistake. I don't know. Okay, so let's say it's something like 2 to 1. And then we do our math, right? Well, no, I screwed up. It's important when you're setting up your conversion factors, I know I say this all the time, but to make sure that it makes sense when you say it aloud as a sentence. And in order to do that, we should probably just get our ratio right. So what is the ratio of magnesium to sodium? Well, there's no number in front of magnesium, so that's a 1, and there's a 2 in front of sodium. So the ratio of magnesium to sodium is 1 to 2. Specifically, for every 1 mole of magnesium, there are 2 moles of sodium. So make sure when you're doing your mole ratio that you get everything positioned correctly on your conversion factor. And then the math becomes really easy, right? We're going to cancel moles of magnesium. Our final units will be moles of sodium. 50 times 2 is 100. 100 divided by 1 is still 100. 100 moles of pure sodium metal are required. So your problems can start at the products and work to the reactants. They could start at the reactants and work to the products, or they could even be within the reactants or within the products, such as if I have 10 moles of magnesium, how many moles of sodium bromide are going to be produced? Well, the ratio is 1 to 2, so that's going to be 20 moles. These mole ratio problems hopefully seem pretty easy, and once you get them down, you're really going to be in a good position to learn the next thing, which is stoichiometry, which is one of my favorite things to teach and is absolutely essential to any burgeoning chemist. So learn this well and then learn yourself some stoichiometry. I'll see you next time.